Welcome. This is the second of our video 34 series. And this one particularly is on the cause for why objects move along a circular path. And it's called the centripetal force, which we're going to talk about in just a second. Before we get to it, though, I do want to point out this here real quick. If we're looking at a quick definition of a term that's used often by physicists, we need to understand what this idea is of uniform circular motion. And so I've put a quick definition here. It's just motion along a circular path at a constant speed. Not constant velocity, but a constant speed. So speed, remember, is different than velocity in the fact that it doesn't have a direction that goes with it. And I think you'd agree that as an object moves along a circular path, like this one, this is a ball held by a string, which is being pulled in a circular path by a hand right here. I think you'd agree that the direction is continually changing as it goes around, even though the speed might be constant. In other words, it may be traveling at, let's say, I don't know, 2 meters per second for the entire path around, but I think you'd agree that it's 2 meters per second going this direction for that instant, and then later on it's 2 meters per second going that direction. So let's say it's right there, now it's going this way. Let's say it's here, now it's going this way. Let's say it's here, now it's going this way, and so on. And so you can see that the direction changes at each instant. And the speed might be the same, 2 meters per second, 2 meters per second, 2 meters per second, 2 meters per second, but the direction is changing. And so that's kind of the point for what we're talking about today here in this video. So we're actually going to do this lab. It looks just like this, only we're going to add one extra little component to it, which is it's kind of fun. Anyway, so you can see here that the reason for this ball moving around in a circular path has to be this string. And the reason for the string causing a force has to be this hand. And so we can trace the forces back if we wanted to, but we're really only concerned about the ball. So let's think about what a free body diagram would look like for the ball. Wouldn't you agree that there may be gravitational force and other things going on, air resistance and all that stuff? But let's ignore all that for right now. Why is this thing moving in a circle? I think you'll agree that it has to be something to do with the string. And the string goes towards the center of the circle. And so therefore, the force that's being applied by the string can only be applied directly towards the center of the circle. So I'm going to go ahead and draw that out. Like so. Right along that line. Like so. And so that's our force right there. And in fact, that's a net force, because that force is causing the ball to move towards the center of the circle, to change its direction in towards the center. And it's that net force right there that's causing the circular motion. If you get just the right net force and keep it constant, keep everything else constant, you can get uniform circular motion, which happens sometimes. That net force has a special name because it is motion towards the center of a circle. It has a special name, and as you might imagine, that name means centripetal. That name means the pull towards the center of the circle, which is centripetal force. The pedal part, I know, sounds a little strange, but the pedal means just towards the center. So like petals in a flower, same kind of thing. Anyway, so we can be more specific about what that net force really talks about if we wanted to, by giving it its own formula. Now, a net force, so this is a net force, right? And so net force, you remember from Newton's second law, says this. A net force is equal to the mass that's resisting it times the acceleration that it produces. Okay, so we could use the same kind of idea, only we can use the easier topics to deal with circular motion. Those easier concepts would be radius and velocity. And so instead of putting an acceleration in there, it might be easier for us to talk about it in terms of speed or velocity and radius. And we'll talk about what that means in just a second. So here's the centripetal force formula. It's one of the formulas that you'll find on the formula sheet. Now remember, this mass right here is a resistance to changes in its motion. But check this out. Isn't that ball changing its motion the entire time it goes around? Yes, it's changing its direction every single instant it's going around in a circle. So is that mass very important? Heck yes it is. It's super important. The more mass there is, the more force you'd have to apply to get it to go around in a circle. I think that makes sense. Okay, what about this is the tangential velocity. If you don't know what I'm talking about, go back and watch 34A. It's all about tangential velocity. So that tangential velocity looks like this. And it's a speed, kind of, but with a direction. And so it's in meters per second. Now, you can imagine the faster you want something to go around in a circle, the more force you'd have to apply. That makes sense. But look, check this out. It's even more than that. That velocity is actually squared right there. It's super important to take that into account. So speed plays a huge role in determining the centripetal force. And then, of course, there's the radius. So if you want it to go in a tight circle, now all of a sudden you're talking about the smaller the radius, the more force you have to be able to apply. Let's go down and talk about something that's probably pretty close to your minds right now, and that's trying to drive your car along a icy road that's going in a curved path like this. So what actually happens? So this is the top view of your car. So you turn your wheels, and your wheels are touching the road, and you are hoping that they have a certain amount of friction. Because what the wheels will do then, although it's hard to imagine this, they actually apply a force towards the center of the circle, like so. And that force is a centripetal force. It's also, though, a friction force. And so on an icy road, you need enough friction to cause a centripetal force. So let's look at what we have here. First off, if you have a very heavy vehicle with a lot of mass, you're going to have to provide a lot of centripetal force. Now, we didn't talk much about this, but typically things that have more weight also are squeezed to the road a little bit harder, and therefore have more natural friction with the road, and so therefore it's not as hard usually to get something that has a lot of mass to turn on a slippery road that's going in a corner or around a bend like this. However, let's look at these two things. Excuse me. Let's say you take the turn too fast. Okay, so you're going too fast around the corner. Look what happens. If this is too large, then that makes the centripetal force very large because it's the speed squared. You have to have a lot of centripetal force to be able to cause your car to go in a circle in this half circular or quarter circular path, which means you're depending on the road to provide a certain large amount of friction. And if it's icy, it can't do it. And so you end up following, instead of a circular path, you end up following your inertial path, which is a straight line. I saw a car do this just the other day, coming home from work. The other thing that you want to think about is radius. If you try to make a very tight turn, it's going to be much, much harder because the smaller this radius is, the more centripetal force you'll have to apply, which means you're depending on the road that might be very slippery to provide a lot of frictional force to be able to turn you. And so these three things are the things that you have to take into account every time you turn your car on a slippery road. The mass of the car, the speed that you're going, and the radius of the turn you're trying to make. You can increase the radius of the turn, and that will make your centripetal force lower. You can go slower, and that will make your centripetal force a lot lower. And then the mass is complicated because more mass actually means more friction usually. So it's kind of a complicated idea. But more mass typically would mean more resistance to a change in your direction, which would mean it would be harder to get it to go around in a corner. You're going to see this when we try to twirl objects around on a string. The more massive it is, the more difficult it is to twirl it around. Now, because we know this, that the net force is equal to the mass times the acceleration, You remember that's Newton's second law. And that net force for an object moving around in a circular path is the centripetal force. You can see that F equals ma, F equals mv squared over r. The a part has to be the v squared over r part. And so technically, there's this thing called a centripetal acceleration. And that's the velocity squared divided by the radius. And by that I mean the tangential velocity. What direction does that act? The net force produces a net acceleration always in exactly the same direction. And so they both act towards the center of the circle. Hopefully that makes sense. And technically it's the centripetal acceleration that causes the motion, and this is what causes the centripetal acceleration. For the sun and the earth moves around the sun in a circular path, and you can see that there must be a centripetal force that's acting towards the sun to get the earth to go around. And of course, that's the force of gravity. And so in this case, the centripetal force is exactly the same thing as the force of gravity. Just like over here, the centripetal force had to be the same thing as the frictional force that was being applied between the road surface and your tires. Okay, hopefully that makes sense. We do have an activity that goes with this that involves twirling things around. So please make sure that you've seen that equation and can use it in certain circumstances. And then don't forget all those tricks that you learned when you were doing free body diagrams. They'll be important for that activity too. Thanks for watching.